So, hello everyone. I'm Ethan. I'm from 26433 Monkey Machina. I'm the only one here today from our team because the other member couldn't make it. But to be presenting on how to decide on a game strategy and then how to execute that game strategy effectively throughout the whole season. So starting from season launch until end of season, how to keep track of the game strategy and yeah. I'll start with who I am. Like I said, I'm Ethan. I used to be on Juniper Robotics from 2022 to 2024. I was a driver and one of the main mechanical designers, the drive team lead, and the driver there. And then now I'm on Monkey Machina. I'm the driver, the mechanical designer for our chassis and slide systems, and our programmer for this season. So jumping in, why is game strategy so important? It's kind of, obviously it's the template for your whole season. But more importantly, having a clear game strategy is very important because it helps you plan your season. If you just say your goal is to score the most points, that can mean a lot of things, right? Especially this year, there's many ways to score points between the different kinds of hanging, the different kinds of specimens, the different bucket heights. There's lots of different options you can go with that. And so by having a specific game strategy, your team will be a lot more focused on these clear goals. And your goals will be successful, or your success criteria will be quantifiable and obvious. So you won't just be like, oh, we did good enough, or oh, we didn't do good enough. It'll be, oh, we were X, amount of seconds off of our target, or X amount of points away from our target, and that's why the tournament didn't go our way. So you'll have a much better sense of like how to orient your team's direction, like, in terms of what you want to work on the robot. And specifically for us, this helped us last year excel on when I was on Juniper on one specific part of the game. So this is our OPR table throughout our season last year. And so as you can see, the main thing we focused on last year was teleop, and I'll get to how we decided on that in a little bit. But as you can see, except for qualifier 3, where we switched drivers to give some experience to a new member, our teleop OPR consistently just kind of increased throughout the season. And that was a direct result of how we had decided on a game strategy. And we were basically every tournament, we would get a whole bunch of data on our teleop, and then we would compare it to where we want the data to be. And then we would take videos in slow motion and analyze how to get us to where we want to be. And then you'll also notice that like our auto and end games were none for some tournaments, or very low. And that's kind of that was a cost that we accepted when we said our strategy is teleop. And so auto obviously wasn't the priority. And we kind of committed to, if we follow through on the teleop portion, right, it won't matter as much if our auto isn't perfect, because we'll at least have a very good teleop. And then if we have even just an okay auto and end game, overall our tournament success will be decent. So like eventually it all came together at Worlds, obviously, in the OPRs. But even at our state championship, our auto only worked about half the time. But we still managed to pull through because we'd focused on teleop, and so we knew that was going to work for us. So deciding on a game strategy, the most important thing I think to note here, especially if your team is not like super experienced or you have a lot of rookie members, is you need to find the right strategy that fits your team. The same strategy isn't the best for all teams. If you're a newer rookie team, even though maybe the fastest possible robot might be, lots of linear slides, lots of motors, servos, and degrees of freedom, you might struggle as a rookie team to build that as your first ever robot. So it might be overall more effective for you to go with a simpler strategy that requires a simpler robot, because you can do better on the execution part. Because it's not just having a good strategy, it's having the ability to execute that strategy. And the big tool that we use to find the right strategy for us is a BVOA, or sometimes it's called a decision matrix, but it stands for best value option analysis. And what this does is it basically allows you to rank different options in a table against different criteria, and you can assign importance to each option. So, we'll get to an example in a minute, but basically the kind of categories you'd have for FTC would be how complex is a task, how repeatable is a task, how consistent is it to be able to do. And then you say, oh, well, complexity is the most important or whatever. So here's ours from last year. So as you can see, this is just for driver controlled and end game. These are all of our options circled there. And then the metrics are to the right of those. And then above the metrics are the metric weights. So repeatability, that was a 5 because we cared a lot about how repeatable things were. because if it's not very repeatable, then you can't reliably get points, and if you're not consistent, you won't be able to consistently win. Points per second, obviously pretty important, but not quite as important as being consistent. Complexity for us, because we had a good number of experienced members last year, we didn't say it was very complex, but this is kind of what I was saying about the right strategy for your team comes in. If I was a rookie team, I'd probably put complexity at a 4, right? And if it's super complex, then I wouldn't really want to go for it, because it might be worth it to just be better at a simpler. It's like, I think this year a good example would be, if you're a rookie team, getting really fast at specimens might be hard, because you have to be really good at both intaking, depositing, and you have to deposit and intake 2 different ways, because you have to intake from the submersible and intake clip specimens, and you have to be able to deposit specimens on the rung. So like, that's an example of where it might be worth it to just, if you're a rookie, focus on samples, and then you can really optimize one intake and one deposit system. And then scalability, which is how many times you can repeat a task. This is because we found that BVOAs can sometimes like lead you astray, because stuff like hanging will rank really highly, because it's like, oh, it takes 5 seconds and you get 30 points, which is a crazy like points per second number, but you can only hang one time. And so if you are able to, have the amount of seconds it takes for you to hang, that's great, but you only do that once. So you only just saved 2.5 seconds. But if you were able to get 1 second off of your cycle time for intaking specimens, you just saved, possibly 10 whole seconds, because you do that 10 times per match. So scalability is a really important category that we always use to weed out the kind of what we call low hanging fruit tasks, where it's like, you do it once, you get a good amount of points for it, but it's not really worth optimizing that, because it only happens once in a match. The next step that we take after a BVOA, and we have our strategy, and from our last BVOA, we took away that we wanted to do pixels on the backdrop. You see that pixels on the backstage was like a low point scoring thing that ranked high, but we it just went with the backdrop, and we then broke down our cycle specifically into like every sub part of what it would look to drive across the field. So we were like, okay, well, to score on the backdrop, you have to drive across the field, deposit, drive back, and intake. It's much simpler this year, or last year, than it is this year. But we then took robots from last year, and we used those to estimate how long each of these should take. And so we would drive the robot across the field, we would time it, we would kind of look at like, okay, well, this robot weighed 15 pounds, and our new one's probably going to not weigh 15 pounds. So it'll be a little bit slower. So we'd add some time there. We would watch videos online and research the intakes and deposit mechanisms from previous years. You can even tie in some prototyping here and look at just explore different options to see what's feasible. Like maybe there's a game challenge where it's very unique, and so there's nothing to go based off of. So maybe you prototype a few different intakes, a few different deposits, and you go, okay, well, our prototypes are saying 8 seconds. And so we think that with some refinement, we can make it 4 or 3 seconds. So that'll be our goal, right? And so you set these very specific targeted goals for just each individual task your robot has to perform. And this is, I think, one of the key things to successfully executing a strategy, because if you're not clear about exactly what you're doing, it's going to be hard to do what you want to do. Like saying, I want to make the robot faster is a very vague goal, but saying, I want to make, we need to drive 1 second faster, because that's why we're not hitting our goal score. It's not in here, but from the breakdown, we then multiply the cycle by how much time there is in a match, and we get a goal score for a season as well. So we try and hit both the goal score and the goal cycle time. That way we have to both be able to physically like cycle that fast, and we have to do it reliably to hit our goal score, right? So kind of from that, with the cycle time breakdown, when it comes to the mechanical team, the cycle time breakdown should really be a thing that they look at quite frequently. Pretty much anytime you need to like design a part for the robot, the breakdown is the blueprint, right? When we went to go make our slide mechanism last year, we needed to be a certain speed. And so we looked at our breakdown. We went, okay, the slides have to extend in this amount of time while we're driving to the board. And then we would go calculate the right gear ratio to hit that time. Same for the drivetrain. We want to drive across the field in this much time. So we would go calculate the drivetrain ratio we needed to get across the field in that time. It's also good for stuff like intakes, because intakes take a lot of iteration usually for your robot. So our intake designer last year, he had his 1 second intake goal that we set at the beginning of the season, and he just spent the whole season. He had like test stands separate from the robot, and he would just iterate the intake over and over and over, and probably 50, maybe 100 iterations of like small parts on the intake until we get down to just that 1 second goal. And so that's kind of like it was like a blueprint or a guiding light as we went through our design process and iterating on our robot. Now some more about the iterative part of the development process. Your robot won't be perfect the first time you build it. Even if you CAD the whole thing, things will go wrong, things will break, things won't be the right speed. Being able to quickly make changes that are effective is important. So, you get your robot together, and let's say you wanted to be able to extend your slides at a certain, or deposit something at a certain speed, but you're not. You're able to quickly figure out why you're not able to do that, and so you can fix it, and not waste too much time kind of dilly-dallying on what other things might be a problem and what might not be a problem. So bringing in the game strategy here really is kind of one of the keys, because now you combine your game strategy with your development process, and you go, okay, well, here's our strategy, and so we can look at what the goals are in our strategy, and then we can directly improve just those things. So the way that we did this on the team I was on last year, Juniper, was we had what we called a client-developer relationship, kind of inspired by the way companies will contract and work with other companies. And so we had a saying, drive team is the boss. So we had a dedicated team of drivers who were all relatively fast. And so they would be kind of judges of new robot features, with the head driver being the main decider on most things. And basically, once the robot was built, programming and mechanical would just give the drive team the robot, and they would just drive it until something wasn't fast. They would time it, and they would get data on it, and they would drive it until something broke, and then they would also look at the data they collected, and they would analyze that to see if it was hitting the drive goals they had for speed, right? And then the robot was only ever changed if the drive team had a request. So programming wouldn't just go in and add features that programming thought would be good for the robot. It would be drive team says, okay, hey, it's taking me, the slides aren't extended by the time I reach the deposit location, right? And so the programmers would go, okay, how can we speed up the deposit? And mechanical would go, okay, how can we speed up the slides, right? And so that way, we weren't making changes that didn't really matter. It's very easy to make a bunch of small changes to your code or to your mechanisms that help a little bit, but they don't really have any impact on your overall robot's performance. So this is how we kept things very focused and very centralized. Is the drive team was kind of the lead of the programming, and the mechanical team is kind of pushing them in the right direction. And the drivers would just get a very good sense of what the problems were with the robot, because it's very easy to look at a robot moving and go, okay, this kind of works if it's just static, but watching a robot perform a whole match and expecting certain performance in a match competition scenario is kind of a whole different game. So that's why it's good to have the drivers look at it. And this ties into drive practice. The biggest thing I would say for teams that kind of have really good robots, but maybe don't perform as well as they could, is drive practicing a ton. And this comes back to the execution, where not only do you need to have good drivers, but if you don't drive to test your robot like you would in a competition, you can't properly predict how it's going to act in a competition, right? If it will be able to execute on your ideas in a real world scenario. So last year we had to run hundreds of practice matches, and we had data and videos on lots of them. We had at least 100 matches where we actually had every single cycle logged and recorded in a spreadsheet, and we ran calculations to figure out who was the best driver and if robot improvements were working. And then additionally, we had a bunch of just video recordings of matches where our drivers would go in, watch them back, and not only look at what they could do better, but look at, oh, hey, I had to pause my driving here because the robot was shaking, or because the robot was doing something it wasn't supposed to be doing. And then they can send that video to the drive team, to the programming or mechanical team. And so this this communication between them is very important, especially when you're drive practicing, and let's say there's a bug in the code that it's never happened before, but it happens one time, right? It's important to not ignore that stuff. Take a picture, take a video, send that to the programming team, in whatever, messaging channel you use, and then have them fix that rather than just like letting it go because it was fine this time, because maybe at competition that issue will pop back up, right? And that'd be a pretty bad time for you to have an issue that you didn't look at before. And then you could have if you had just noted the stem. So don't let small things like slip by, and make sure that driving is a priority and not just like something you do when you have extra time. It's like for us, the reason that we didn't have autonomous for a lot of our tournaments previously was because we looked at it and we were like, we would rather drive practice for a whole week to fix every mechanical bug and programming bug on the robot than have any autonomous at all. And that was the right decision long term, because over time that drive practice stacked up to us having solved pretty much every problem with our robot. Like we had only one failure on the robot the whole year in terms of mechanical or programming, and it was dust on a sensor. Everything else, there's no wires coming unplugged or code bugs that broke the robot or parts breaking mechanically that like weren't supposed to. Like everything was right, and that's because we were able to just drill down the basics of our robot, and then we added on autonomous stuff afterwards. Obviously, they weren't as fancy as some of the other autonomouses that we could have made, but executing one thing really well really helped us last season. So what this looks like kind of in practice, these are just screenshots from our judges presentation last year. But as you can see, like the goal for our robot last year was after we crossed the halfway line of the field, we had to be able to extend our slides and put our arm out before we hit the end of the field so we could deposit without having to wait for the robot. So we had these certain second extension and retraction goals for our robot. So when we made the slides, we calculated the right gear ratio. And over here for the intake, the first one is a 1 second intake, which is like a physical requirement. So that was the 3D printed parts for the robot help us do that. And then below that is the 0 button intake and the prevent pixel jamming. Those are stuff that the drive team requested. The drive team was like, hey, there's too many buttons for the intake. And that's slowing us down. And so they said, okay. And the programming team went and they used sensors to automate the intaking process. And the drive team went and said, hey, mechanical team, there's pixels getting stuck in the intake. We can't intake. Hey, this isn't working. And so programming team went and then they iterated the intake to have pixels automatically move around and slide into position on their own without anything else. So this is kind of like what the kind of what it should look like if you're implementing these practices and processes correctly. Is you'll have these kind of like goals or problems, and you'll have very clear solutions to very clear problems, rather than like kind of like lots of little problems that like are solutions to problems that didn't exist, stuff like that. Well, that's all I had for the decision making and strategy. So if you guys have any questions, that would be great. And thank you for listening.
I have one question. What methods do you use to evaluate the strengths and weaknesses of your robot during the season?
That's a really good question. Let me see. I don't think I have it in here, but it kind of goes in with this cycle time breakdown and our drive practice thing, where every driver we had 50 matches of recorded data, and we would break that down into custom metrics. So we had these two things called a capability score and a consistency score. And so basically it was, we would look at data, like last season was how many mosaics they made every single match, right? And we would have that number of mosaics, and we would also have how often, we would like record how often they dropped a pixel on the ground, or how long it took us to intake, or how long it took us to deposit. And so we would have composite metrics where we would do, I'm not sure about the details of it because we had a statistics guy do that, like on our team. But basically, we would take all that data and then we would compile it into just two numbers for how capable and how consistent it was. And then at every benchmark tournament, like right before every tournament, a few days before, we would record a whole bunch of data and then put that in a chart. And so we would be able to chart over time at every tournament. Did we have an increase in capability? Did the robot get less consistent? And that would kind of line up with, it's because we rebuilt the robot and it has more problems than it does before. So sometimes it's like less consistent, right? So it's all data based. It's not really subjective. It's just we put it data, we chart the data, and that's how our robot's doing right now. And we just try and increase that. Hopefully that answered your question.
Thank you.
I also have a question. How do you adapt your game plan when facing unexpected challenges in matches?
Um, Yeah, that is kind of the one struggle that we kind of had last year was figuring out how to adapt to other teams. Last year, what we did was in our home state, we just kind of at our first qualifiers we tried a few different things, and we just found that statistically, it would always be best to run a certain strategy where we would do most of the scoring, and our partner would just give us pixels and put them next to us, and we would actually put them on the board. So usually we try and have that data beforehand, and then we can, like, if we have a partner and we tell them, like, yeah, um, then we can be like, hey, we think this is the best strategy, and here's the data on it. And they'll usually, if you can provide data, they'll agree with that. But then if for the during the match kind of situations, we did this thing we call human versus robot, where basically we'd have our robot on the field and we'd have our drive coach on the field, and he would act as another robot, and he would just do the most obnoxious things. He would get in our way. He would knock pixels off the board. He would break the rules on purpose. And basically, it'd be the driver's job to keep cycling at the same speed we were designed to cycle at while all these things are still happening to the best of his ability. And it wasn't, and so it was kind of, it was an unfairly bad situation for the driver. And we just practiced still being able to compete in these adverse conditions. And that's how that went. And so, yeah.
Thank you. Can you share an example of a key strategic decision that changed the outcome of a match?
A key strategic decision that changed the outcome of a match last year. I'm trying to think of one. Really, we only had a handful of matches last year where we didn't run our planned strategy because it was so practiced and kind of reliable. We were able to count on it pretty much all the time. But I'm trying to think of a time where last year, I guess our state's finals, in our first finals match, we had a chain that was zip tied together to hold tension, and that zip tie snapped at the end of autonomous. So our robot was totally disabled for teleop. So we quickly pivoted to playing just super hard defense on the other team, which was something that we had a little bit of practice with because we'd practiced against the human versus robot games where the human would just stand in front of the robot in the most obnoxious place, and we'd have to drive around it. So we kind of knew how to play good defense. And so we were actually still able to win that match by like 40 or 50 points, even with just one working robot, because we knew how to just like instantly, no time wasted. We pivoted defense, and then our drive coach actually started drive coaching the other team to help them cycle even faster, since there was no point to helping our team drive coach. So yeah, that was kind of the big thing.
Thank you.
There's a raised hand, I guess.
Hello, I have a question. What would you say we could do if we didn't have enough money to test our robot enough because of worn down motors and servos and such?
Yeah, that's definitely a tough question. I think one thing that we do is we have like sub-assemblies on our robot. So like last year, our intake would just come totally off, and we could test that separately. So like, let's say if you wanted to like really test your intake, you could. I mean, I don't know what your team has, but if you have like a drill, you could like use a drill to run your intake to test the intake separate from the rest of the robot, and so you save your main motors for competition. For like stuff like depositing, that's kind of tricky. I mean, if from a drive practice standpoint, there's video games you can play. I think there's a simulator for FTC games, but like mechanically testing and program testing, I would suggest kind of isolating subsystems and testing them without FTC parts. So using a drill to power your intake, or in programming, having like a testing environment where you can simulate like subassemblies and like input output test. in different scenarios and like do a lot of code tracing and practicing in that way, so that hopefully when it comes together, you don't need to do too much on robot debugging. But yeah, that would kind of be, yeah, isolating down problems and testing them individually would be my biggest advice for that kind of situation.
Yes, thank you very much for your answer.
Are there any other questions? I think there are not. Well, then we really want to thank you for taking your time and sharing this amazing information with us today.
Thank you for having me. This was great to connect with teams internationally. It's always fun to do it in person, but virtually is great too. So I'm glad we got to meet some new teams, and hopefully I'll connect with some more of these teams later in the season.
Yeah,
Thank you so much.
Thank you so much.
Bye bye.
Bye.